Hello guys, welcome to week 4 of mathematical applications. Today we are going to look over data analysis. All right, so my name is Mr. George. Always feel free to ask questions. Yeah, sure. Approve. Okay, whatever. Okay, so my name is Mr. George. Always feel free to ask questions. And today we will be learning about graphs and how to read them, important statistical vocabularies, and data inferences. Oh boy, okay, that's a lot of note takers. It's fine. All right. So if you have any questions, feel free to send it in the chat or use the raise your hand function, or just say something when I'm not talking. All right, guys. Perfect. All right. Okie dokie. So graphs. What are graphs? Graphs are visual representations of relationships between two or more variables. So here we're going to go over different types of graphs. So first of all, we have the bar graph, right? So this is a proportional representation of magnitude in certain aspects. So basically, for example, here is a graph to show people's favorite day of the week. And so if you guys can see, more people love Tuesday than Monday, right? So that's what that means. More people love Tuesday more than Monday, but more people love Monday than Wednesday, and so on and so forth. So the size over here is going to be basically proportional to how much quantity of something is when it refers to down here, all right? So in the next one, we have our pie graphs, right? So pie graphs show frequency or proportionality of a variable within a whole in comparison to other components. So basically, what you have to envision here is basically that each one of these, what this is, it's just a pie, right? And you can slice the pie different ways, and the size of the different slices is going to be proportional to the magnitude of a certain variable within a whole, right? For example, we have a sales chart, right? So the entire pie is going to be pretty much what the sales are, right? And this bigger slice, furniture, that is 42% of all the sales. So that means that furniture is a big portion of how much this certain store sells. So over here we have the line graph. Pass this over here. Okay, so over here we have the line graph. So these are mostly used to denote change over a variable, normally time, in comparison to another variable. All right, so if you guys want, you guys can get a piece of paper. I forgot to say this in the beginning of the class, but you guys don't really have to get the Google Doc out. If you have it out, then that's very good. But I would suggest you guys get like a piece of paper over here. Get a piece of paper, or just try to screenshot some of this. I'm gonna send this presentation out when I'm done. All right. So here's more types of graphs. So over here we have a scatter plot, right? So it uses dots to represent value pairs, meant to portray and generalize a natural relationship. So here we have this scatter plot. It shows here we have the number of, all right, whatever. So here we have on this axis the number of visitors, and here we have on this axis the daily temperature and visitors for 90 days. So it's kind of like the line graph. So which denotes the change of variable over time. And so here we have these straight lines, right? But here we have a lot more data points right here. We have a lot more data points. So what that tells us is that each one of these data points is a certain like actual thing that actually happened, right? Each one of these is an actual like value that is real, right? So somebody or somewhere in this park, right? So one day, the daily temperature was what, 85, around 85, and the park got like around 500 or 50 visitors, right? So that is an actual day. So these help us represent actual real life values. Over here, we have the box plot. Now, this one's very special. So it uses its sectors to denote the distribution of values against other variables through quartiles. So what a quartile is basically like if you divided a population into 4, right? So if you have 4 segments of the population, right? The top segment, so for example, we can say this using test scores, right? So here we have the different test scores, a teaching method. So here we have different types of teaching methods, and here we have the scores, right? So this long one is going to be the first quartile, right? So the first if we say that we have 100 kids, right? So in the first 25, the highest 25 are going to be here, right? And then they're gonna have their scores are gonna have a range between 30 and 40, right? And so then the next 25, they're gonna have a range, a smaller range right here. And then so then the lower 25, they're gonna have like a little range down here. And then the last 25, the 25 lowest scores, their range is represented through here. All right. So that's basically what this is saying. So it's also called a box and a circle. So here we have a histogram. What is a histogram? So it's like a bar graph, but it's used to denote a frequency of a value in a certain data set, right? So basically what it's saying is that here we have this many people that are between the ages 60 and 70. So 670. All right. So it's basically saying that there are 3 people in this data set that are between the age of 60 and 70. So here we have another line over here, 50, 60, right? So that means that we have 5 people between the ages of 50 and 60. All right, so that's basically what it's saying. So more on box plot, right? So the introduction to the data analysis using the box plot. So basically here we have the minimum, right? So yeah, here we have the minimum. So this is a certain amount of people, right? And so here the lower quartile, so the first quartile begins, right? So what that means is like the first amount of people, oh boy. Yeah, so the first amount of people, so the first 25 people are going to be here. And this is going to go through all the way to the third set of the 25 people. I was mistaken back there. I was wrong. I was thinking about something else. But here, I have the upper quartile of so we have 25, 25, 25. So those are 3 quartiles, right? So that basically means we have 75 people in here, right? And this little line here, that denotes the median. We're going to go over what that median means. We're going to go over what that median is later. But here we have the interquartile range, and here's the maximum. So the maximum is the greatest value that we have in the box plot, right? So over here, we can say that 25% of the data are above 4 to 3, and thus the upper end of the box is the third quartile. In the box, we find 50% of our data, right? All right. And 25% of the data is below Q1. So the lower end of the box is the first quartile. All right. So yeah. So yeah, so within the box, if we have 100 people, that means that 50 people are going to be within this box. And then 50 people are going to be outside here. All right, so we have here a representation of I was mistaken, that's my bad. Yeah, so here we have a visual representation of this through the standard deviation. So basically what that means is that here, 50% of everybody is going to be inside this little box plot, right? So 50% of people are going to be in this little box plot. So that means that 50% are going to be outside here. That's basically what it's saying. So we are going to look at the anatomy of a graph. So here we have the title. The title is going to be okay. We have to chat. I guess it's the AI assistant. Okie dokie. Okay, so here we have the title. So it's probably always going to be the denotation of the y-axis versus the x-axis. So here we know that the y-axis is the dependent variable or the unit, and here we know that the the x-axis is the independent variable, and we know the unit. So first of all, the independent variable is the variable whose value is not dependent on the other's value and can be manipulated to change the dependent variable. So whatever change is happening here, that change to the function is going to affect directly the y-axis, right? So here we have the independent variable, which in this case is time. All right, let's see who else is here. There's just there. All right. So here we have, and then over here we can denotate the dependent variable. So the dependent variable is the variable whose value depends on the value of another variable, which is presumed to be the independent variable. So the value of this, so the value of the y-axis, the value here that is presented here depends directly on the value that is given down here. So for example, we have 180. Well, depending on this function, right? If we put 180 through this function, we're going to get out 610. right? So that means that the x-axis, the y-axis is dependent on the x-axis. So that means that displacement is dependent on how much time has passed here. And something that we always have to do, we always have to look is when different graphs have different unit quantities, we have to pay attention to them, especially in slope and change calculations. So we have to look at these different units. So each one of these little boxes, right, it's something different on the x-axis versus on the y-axis, right? So each little box over here is going to be 30 seconds. And each box over here, up here, is going to be 20 meters. So that's something that we have to consider and we have to take in mind before we do any calculations or do anything with things. So here we have an example of the dependent variable, right? So the dependent variable responds or depends on the independent variable. So independent variable, amount of light the plant receives. So this is the cause, this is controlled, and this is graphed on the x-axis. Now the dependent variable, it's the actual plant health. This is the effect, this is measured, and this is the graph on the y-axis. So this is basically saying that the independent variable, it's what is controlled in an experiment, and the dependent variable is what is measured in the experiment. Okay, let me see. Oh my gosh. Okay, we're gonna clear this. I'll draw. Okay. So here we have the bar graph above shows the number of sunny days in 2019 for 4 towns. How many sunny days did Dustville have in 2019? So the first thing that we're going to want to do is we're gonna want to look at Dustville in 2019. So if we look over here, oh sorry, I have another. Okay, so we want to look at Dustville 2019. Okay. So Dustville 2019, and if we set the line over here, right, that's going to give us 100. So we just have to look at the x-axis, which gives us what town it's talking about, and then we just take a look at the y-axis to see what value corresponds with it. So the value that corresponds with it is 100 days. All right, that's pretty easy. That's very, very, very easy. All right, so we're just going to look at what else. So Paulina bought her first video game in 2014. She bought her first video game in 2014. So the line graph above shows the total number of video games Paulina owned since then. According to the graph, the number of video games she owned in 2015 is what fraction of the number she owed in 2019. That sounds like a lot of words, right? But what we have to do, what we are just doing, is we can disregard this, right? Bought her first game in 2014. That's only denoting what year it is after that, because this, if you see, this graph isn't always in what year it's in, right? It's years since 2014. So 1 would be 2015, 2 would be 2016, and so on and so forth. So that's basically what that's saying, right? So according to the graph, the number of video games she owned in 2015 is what fraction of the number she owned in 2019. So we have to look at the two data points between the amount of video games that she owed in 2015 and the amount of video games that she owned in 2019. So 2015 minus 2014, that's 1 year. So that's 1 year of difference. So here we have 5, and then here 2019. So the difference between the number of years of 2014 and 2019, that's going to be 5. And so we have here 5 versus 15. So considering that the graph is in years between years since 2014, to find the corresponding x value, we need to subtract the needed year from 2014. Okay, so here we can denote that it's 5 and it's 1, and here we can denote that this is 15 and it's 5 years. So in 2015, it was 1 year later, and she owned 15 video games, right? And so in 2019, it's 5 years later, and she owned 15 video games. So we can set the equation up as the fraction. So it says the amount of video games she owned in 2015 is the fraction of what? Of 2019. So that basically means that we just need to set this one above this one. It's 15. It's 5 over 15, and that equals 1/3. So that's very good. Right. So what I want to look over, what I want to look here is the normal distribution. So you guys are going to see this a lot when you guys get older and you guys look at a lot more stuff regarding, hold on, wait. Okay, when you guys look at a lot more stuff regarding statistics and looking other stuff. So average distribution of any histogram. So this is the average distribution of any histogram. So this is like the most average ever, right? So the most average score or the most frequent value is in the middle. So the frequent value, so we can see over here, right? So if you guys don't know, the SAT is a standardized test that is used for college admissions, right? So here we have in the middle, right? In the middle, the most average score, right, is going to be the 1150, right? So that means that the average score, so like if you take everybody's scores and you average them out, then the most normal score, like the most, okay, that's the average, that's like in the middle, is going to be 50-50, right? And so is in the middle, and as larger or other smaller values diminish in frequency, they become further from the mean. So here we go, here we can see that this score 1600, which is considered to be like a perfect score, is going to be very, very, very far from the actual middle that we have here. So yeah. So what this measures is the standard distribution, or how spread out the data is in the average. So here we have a normal distribution, and so there's a lot of distance just physically between this and this right here, right? There's a lot of distance, and there's a lot of distance on the other side, right? If you go to 700, which is a pretty bad score, if you go all the way down here, there's a pretty big distance, right? And you can see in all of these that each one of these little clicks right here, boom, 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 it is one standard distribution, or the distance between the mean. So we are going to look at what actually is the mean. Okay, so here we are going to look at some vocabulary of statistics, right? So here we have the centers. So the centers are the typical values of data sets, right? So there are three types of centers. There's a mean. So the mean, what a mean means, what that means is basically that is literally the average value of a data set, right? So the mean is equal to the sum of the values over the number of values. So for example, all right, so actually I'm gonna give you an example. So in this course, we're just gonna say that this symbol, which is sigma is equal to the sum. So whenever we say sum of values, I'm just gonna use this because it's quicker, right? And n is going to be equal to the number of values, right? So here we have an example. So let's say each one of these represents the amount of pieces of gum that each one of you and your friend group eats. So let's say somebody eats 2, another person eats 2, you eat 5, another person eats 3, another person eats 5, another person eats 7, and another person eats 4, right? So if you want to see the average amount, like if you guys had to like decide on like, okay, this is the best amount for everybody, if you guys had like limited, you guys are just going to plug it into this equation, right? And get the mean. So then that means that it's all going to average out, and you guys are going to have the same amount without having too much deviation to each side. So basically what this means is we're going to solve for sigma. Sigma right here, this is sigma. And so we're going to solve this by adding all these values, because remember we have the sum of values, we add that and that equals 28, and n is equal to 7 because n is equal to 7 because we have one value here, 2, 3, 4, 5, 6, 7. We have 7 values. I'm so sorry, my 7 is not very good. So we have the 7 values, and that is why n is equal to 7. Boom. And so then now we just divide these two. We have sigma and n, and that equals 4, and that equals the mean. All right, guys. So that is basically what we are doing. 28 over 7, that is equal to the mean. All right. So another type of vocabulary that we're going to do is the variation between the data sets, right? So there are two, this is called the spread. It's variations within the data set. So there are two different types of spread, right? We have the range. And so the range, what it is basically the difference between the maximum and minimum value. So the range is equal to the greatest value in the data set versus the smallest value. So for an example, so we have the same data set that we had over here, right? The amount of gum, sticks of gum that we all eat, right? So if you want to know the range, we're just going to take the largest value, which in this case is going to be 7, right? Because 7 is the greatest out of all of these. And then we're just going to subtract 2 from it. 7 minus 2. And that gives us a range of 5, because that's just how it works. All right, they're all drawn. All right, let's go. Okay, so now we're going to go into some more vocabulary. So what is a median? So a median is the middle value when the data set is ordered from greatest to least. So if the number of values is odd, the median is the middle value. If the number of values is even, then the median is the average of the two middle values. So for example, that was a lot of words. What does that all mean? So for example, we have this data set, right? So 3, 10, 8, 5, 6, 3. So what this can literally be anything. But if you want to find out the median, we're just going to order these from greatest to least, from least to greatest, sorry, from least to greatest, right? And so we want to see what is the middle value when we order them greatest to least, right? So then that means we're going to cross off this one. This is just a strategy. So, right? So we're going to cross off this one on this side, and then we can cross off one on the other side so that we are left with in the middle to try and find out middle value. So we're going to cross off that one from that side, and that one from that side, that one from that side. And so that means that the median is equal to 6. Yeah. Hold on. Wait. Okay. So, yeah. All right. So we have here another data set. Yeah. So here we have another data set. We have 7, 6, 4, 8, 10, and 13, right? We're just going to order them from greatest to least. And 4, we're going to knock off this one. So there's another, that's whatever. Knock off that one. And so now here we have to average out these two, right? So the average is going to be between these two, right? So we're going to add 7 plus 8 over 2, and it's going to give us 7.5. So standard deviation. So what is standard deviation? So standard deviation, we already talked about it. We said that it was the average distance between the value and the mean in the data set, right? So the calculation for standard deviation is too complicated for class, so we can still study its effects. So for example, here we have 2 standard deviations, right? 2 different ones, right? So we have these curves, right? And so we can see here the standard deviation is 10, right? So that means that the values are more spread out from the mean here on this graph than they are on this graph. So this one's a lot skinnier, but it's a lot taller because more of them are frequented around the mean, right? And so the values that are far away from the mean, they are represented with 1 standard deviation, minus 2 standard deviation, minus 2 standard deviation. So that is the distance that they are from the mean. So which graph right here has a smaller standard deviation? Who can tell me which graph over here when we are talking about, okay, we have 36 things. Okay. Okay, what are we doing? Okay, I'm just gonna ignore that. Okay, let's not spam in the chat. All right, so here we have these 2 standard deviations, SB10 and SB5. So who can tell me, raise your hand or blurt it out, which one of these has a smaller standard deviation? You can tell me.
Which of them have a smaller median?
Has a smaller standard deviation.
Um,
From the purple one and the red one.
the purple one and the red one. The red one.
Now, why would it have a smaller standard deviation?
Because wait, let me think. Let me explain. Wait, I don't know. Wait, let me.
Well, think before you answer. So basically, the smaller standard deviation, right? The standard deviation is given right here. It's 5, and we also have 10 right here. So the smaller deviation means that it's the things that the values are closer to the mean, right? So that means that the further away they are, the greater the standard deviation, right? So you can see this graph is a lot fatter, and there are values that are more further than the mean than this one is, right? So knowing that, Layla, which one of these has the smaller standard deviation? Layla, so which one of these graphs has the smaller standard deviation?
I'm not sure.
All right,
Wait. Go.
what do you not understand about this concept?
Um, mm,
Standard deviation is given right here. So this one has the standard deviation of 5, and this one has a standard deviation of 10. So which one has a smaller standard deviation?
Oh, so the purple one.
The purple one, right? But how is that shown in the graph?
Because the let me check the mean. Is it because the mean of the purple?
No,
Wait,
they have the same mean. They have the same mean. So it's the average distance between a value and the mean in the data set. So all these values, each like the space under the graph is a value, right? So if we can take all the space, those are values, right? But that just means that these values are closer to the mean. That's why it has a smaller standard deviation. Please be paying attention, all right? So we have to be paying attention that these values are closer to the mean because they're just not that spread out. So if we say that both of these graphs have the same number of data sets, or both of these graphs have the same number of data points on them, right? Then that means that this one is closer to the mean because it's skinnier, right? So we have the walls that are skinnier, right? And that means that they're closer to the center. That's the same thing between the values and the mean in the data set. So the fatter one is going to be more spread out. All right. All right, let's just go on. Okay. The purple one, because its values are closer to the mean. So remember this, if you guys remember anything from this lesson, please remember that a smaller standard deviation means that the values are closer to the mean. All right, okay. So here we have another vocabulary word. So what is the mode? A mode is the value that appears the most frequently in a data set. So a data set can have no mode if no value appears more than any other, and a data set can have many modes. All right, so for an example, so we have here a data, right? So it's 1, 4, 3, 1, 4, 4, 2, 3, right? So we order them here, we can see 1, 1, 2, 3, 3, 4, 4, 4. That means that 4 is listed here 3 times, and 3 is only listed 2 times, 1 is only listed 1 time, and 2 is only listed 1 is only listed 2 times, and 2 is only listed 1 time, right? So that means that because 4 is listed 3 times, it has the greatest amount of frequency, so that means that the mode is 4. So here we can see an outlier. So an outlier is a value in the data set that is significantly differs from other values, right? So the inclusion of outliers in data sets can greatly skew these summary statistics, which is why outliers are often removed from data sets. So the inclusion of outliers increases the spread of data, including leading to a larger range and standard deviation. Conversely, removing outliers increases the spread of data, leading to a smaller range and standard deviation. So here we have, all right, I'm just going to go through this. We have 10, 10, 12, 11, 13, 12, and 48. If you guys look at here, all these are in the 10s, 12, but here we have a number of 48. So if we want to calculate the mean, right, so it's going to be the sum of all of these numbers plus 48 over 7, because we have 1, 2, 3, 4, 5, 6, 7 numbers, right? And so that's going to give us a mean that is 16.6, right? But then if we disregard 48, we say, oh no, that's an outlier, right? And we disregard it. So that means that the mean is going to be the sum of all of these numbers over 6. And that means that the mean is going to be 11.3. And it's going to be a lot different, even though it's just one data point, all right? Graphical application. So a box plot summarizes resting heart rate and beats per minute of members at a gym. What is the range of resting heart rate? So who can try and answer this question? Try and answer this question. Anybody? You can raise your hand or say it in the chat. Go ahead. Anybody just try and solve this.
The range is
Yeah. Wait, first of all, define, do you remember what range is, Layla?
yeah, the range is the maximum, or like the max minus, the highest value minus the lowest value.
Very good, very good. So now if you look over here, the box plot, right? It tells you the greatest value and tells you the smallest, I'm so sorry. Tells you the greatest value and tells you the smallest value. So using that, what is the range? Approximately, what is the range of the heart rate?
It's like, wait, 100 minus, like, is that, do I have to do, okay, like 60-ish?
That's around 60. Very good, Layla. All right. So here we have the the greatest value, the smallest value. So remember the range, the largest value versus the smallest, right? And so 101. Okay, so you're off. It's very small, but it's going to be around 60. So it's 62. All right. So that's how we calculate the range. All right. So all right. So I'm just going to explain this one. The graph in the 2D plane shows the diameter D in centimeters of cactus in the Atacama Desert of Chile, H hours after midnight. What is the best interpretation of the D intercept in the graph? So if you remember, I'm not sure if I explained this, but the y-intercept is when time is equal to 0, right? So that is when the y values start. So that is a y-intercept, right? So, okay. So, the y-intercept here is going to be 28, right? So the y-intercept always represents the output value when the input value is 0. So if we have the time in hours and the time of hours is equal to 0, right? And of a cactus in the Atacama Desert in Chile, H hours after midnight, that means that it is 0 hours after midnight. So that means that it is at midnight, right? So see that the X values are in hours after midnight. In this situation, in this situation, the cactus's diameter is 28 centimeters at midnight, because here we have, it says on the line that it is 28 centimeters at 0, which means that it is at midnight. All right, so I'm not going to make you guys do this one. So based on this table, what is the median of the data? So here we have n is equal to the amount of terms. How do we calculate the amount of terms, we might say? All right, so n is also equal to the sum of frequencies, because what frequency basically means is just the amount of time something is in the data set, right? So if we see here, right, so we have the value 119 appears 3 times in the data set. The value 121 appears 4 times in the data set, so on and so forth. So n is the amount of terms, n is equal to the sum of frequency, because each one of these has 1 term. 119 has 3 terms, and so on and so forth. So we're just going to have to add all those. And now here, this might look like a complicated thing, but we can calculate the median based on the average of the frequencies, or the middle frequency, right? So if you have this many frequencies and we layer them going up, right? In the middle, right? In the middle. So let's say each one of my fingers is one type of frequency. So boom, 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 and it just so happens at 10 in the middle, right? If we look at it visually in the middle, that is going to be the median, right? And so we can apply this right here. If we have n amount of frequencies, so in this case, it's going to be 10 fingers, right? And we're going to divide it by 2. So if I have 10 fingers divided by 2, that's going to be 5. That means that the median amount of fingers that I have is going to be 5. All right, but here, this equation is for, it's for the median. So this is equal to the median. And the frequencies counting up can be set as the terms in the sequence. So if we have it here, so 1 plus 3 plus 1 plus 4 plus 1 plus 2 plus 1 plus 6, fine, just adding up all of the frequencies, right? Because that is just the amount of terms that we have. And so that is 19. And so 19 plus 1 over 2. So then that means that the 10th term in this frequency array is going to be our median. And that's just kind of logical. You can raise your hand if you don't understand. This is kind of abstract. I'm not gonna lie. This is very abstract. And if you do the homework, please do the homework. It's gonna be a lot easier to do it. So if we have here, right, 19 plus 1 over 2, that's going to give us 10, because the 10th term is going to be the median. So if we count up from here, the 10th term is going to be 123, because if we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because we count it up from going up from here. If you guys understand this, it's okay if you don't. I can explain it a little bit better. You guys understand this? You guys can say something.
Yes.
You understand this? Okay, Ebenezer, do you understand this somewhat?
Yes.
You understand this? It's okay if you don't. It's pretty abstract. Okay, this is fine. All right. It's going to be the nth term in 123. So that means that the median is going to be 123. Perfect. All right. So Elena mailed 6 packages with the following shipping charges. 6.15. So we have all these numbers. So if she mails a 7th package for $5.61, how will that affect the median shipping charge? So, guys, what is the median? What is the median? Can you remember what the median is? All right, Ebenezer, what is the median?
Where's the set?
Where is the median? Or what is the median? Define what a median is.
$4.41.
I mean, yeah. I mean, I guess in this case, so like, just tell me what the definition of median is, like in general.
It's a median is like the for example, in a set you have like a bunch of numbers, and the median is like the number that's like straight in the middle.
That's very good, Ebenezer. You were listening. Thank you. All right. So if she mails a 7th package for $5.61, was the median shipping charge? So we are going to set this array. We have the set of numbers, and we're just going to set it in a line, right? So greatest, we're just going to set it least to greatest, right? And so we're just going to knock off 1 and 1 and 1, and we are left with these 2 numbers, right? Because this has an even amount of terms, right? 1, 2, 3, 4, 5, 6. 6 is even, so we're just going to add these 2, and we're going to average out. And so then the median without this package. So remember, this is 6 packages, and this is the 7th package. This is without the new package, right? So then we have this average, and the average of this is going to be the median, right? But if we add 5.61, right, we're just going to plop it right in here, right? And we're going to do the same thing. We're going to knock off, boom, 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 boom. But this time we have a middle, right? Because we have a 7-term set. So what that means is that the amount of terms is going to be odd, and it's just going to be the middle. So that means that the new median, if we add this package, is going to be $5.61. So if we find the difference between this median and this median, that's going to be 5.61 minus 5.20. And that's going to be the difference is equal to 41 cents. So the difference between the median, if you mail a 7th package, is going to just be 41 cents. All right, that's very good. All right, application of graph. So in this graph, which is bigger, the mean or the median? All right, if anyone wants to take a crack at this, go ahead and raise your voice. See what we can come up with. This one's kind of fun. This one's kind of fun. Actually, first of all, who can tell me what type of plot or diagram this is?
Can I answer?
Yeah, go ahead,
The
Sarah.
dot plot?
It's not exactly a dot plot because we don't really have an independent variable here. This is a histogram because it denotes the frequency, right? So we have student height distribution in inches, right? So here we have 65 inches. There are going to be 5 people that are 65 inches tall, right? And there are going to be 4 people that are 68 inches tall, right? And yeah, and so we're going to have no people at 77. So here, which is bigger, the mean or the median? So if we can count the median here by knocking off 1 on here, 1 on here, because we want to find the middle one, right? So it's going to knock off 1 here, 1 here, 1 here. That's a lot of stuff. So in a symmetrical graph, so this is not a symmetrical graph, but in a symmetrical graph, the mean and the median are the same. Because the values are at the rightmost area of the graph, the mean will be larger where the mean will be larger than where the largest number of dots are concentrated. So here we have a lot of concentration. So here we have more values over here on the lesser side than we have on the bigger side, right? So that means that the median will be more over here, but the mean, because of these bigger ones, is going to be more over here. Because remember, we add all the big values and we jumble them all in the same group as the smaller values, right? So the larger number of dots on the left side suggests that the median will be more to the left than the mean. This is kind of abstract, so if you don't really get it, that's okay. It is safe to deduce that the mean will be larger than the median because the mean has different properties, right? So we have to include these ones, but on the median, these ones have less effect on its value. So graphical inferences utilizing scatter plots. So scatter plots are normally representations of quantitative data. So information that can only be measured or counted can be measured or counted and expressed numerically. So it represents quantities, amounts, or ranges, and is used for mathematical calculations and analysis. So what is the line of best fit? The line of best fit is an approximate line that fits the general trend of the graph. So we have here what the heck? Okay, that's my bad. Okay, so we have a graph between cost versus weight. So here we have weight as the independent value, and here we have cost as the dependent value, right? And so we have all these values, right? All these little independent values. So the line starts up at the origin, goes up linearly. Its data points are close to the line of best fit. The line of best fit is we're just going to be striking a line through this this scatter plot, and it's just going to kind of follow the general trend, right? And so here we can say that because all of the little dots are close to the line, it has a strong positive correlation. Why is it positive, you may ask? It's because the line is going up. It's going up. It's going up into the air. So if it's air, then it's mostly a positive correlation. And we'll see here that this is a negative correlation. But this is strong because it is closer to the line of best fit. So now we have here, right? So what we have here is, okay, not the, okay, so we have the kilometers run per week versus the weight, right? So here we have a bunch of little dots over here, but we can see that this line of best fit, right? The dots aren't that close to the line of best fit. So then using this and other clues, such as that the line starts far above the origin, that there is a general trend downward, right? We can see that the line is pointing downward and the data points are dispersed from the line of best fit. We can say with certainty that this is a weak negative correlation. It is negative because it is going down, and it is weak because the dots are not very close to the line of best fit. All right. So here we have some more stuff, right? So here we have an example of strong positive correlation, right? Because it's going up and it's close to the line. And here we have an example of strong negative correlation because it's pointing down. But both of these are strong, right? But both of these are strong because the dots are close to the middle, right? But these ones, on the other hand, these ones, the dots are not that close. They're further away from the line. Right, these are further away from the line, and this one has a positive correlation. This one has a negative correlation. So this one's pointing down. This one's pointing. Here we have other things, but a scatter plot can also have no correlation because the dots are just spread out everywhere. So one can use the line of best fit to make predictions. So here we have a review of the slope. You guys can use this later. So I'm just going to walk you guys through this. So the scatter plot above shows, or below, shows data from a random sample of people who reported on the age and mileage of their cars. So a line of best fit for the data is also shown. Based on the line of best fit, which of the following is closest to the predicted mileage in thousands of miles of car that is 13 years old. So here we have the car age versus the mileage, right? So here we have the equation. We don't really need the equations, but because this line of best fit is a slope, right? It is just a general line. We can just line up our independent variable or x-axis and look at it. But I think the graph here ends at 12, right? So then that means that the y is equal to 12x plus 5, right? So then that means that the independent variable or the mileage of the car is equal to 12 times the age of the car plus 13. So we can just plug this in using this equation that is given and find out the amount of mileage, right? So if we have 12 times 13 plus 5, that's going to mean that the mileage is going to be 161,000 miles, right? So here we have another scatter plot, right? So the scatter plot below illustrates the relationship between the number of students spent studying and their test scores. What is the best prediction of the score of the student that studies for 1 hour? So here we have the independent variable here, which is the study time. And here we have the dependent variable here, that is the score, right? And so we can just kind of line it up here, but that's not very clear, right? So we have to determine the unit. So 1 unit of the x value is going to be 0.5 hours, right? 1 unit of the y value is going to be 5 points. So we have to draw the line of best fit. So if we're going to draw the line of best fit, we're just going to plop it right down here, right? And so we could look it up. So find the corresponding x value, find the value that it asks for in hours. So here we have 1 hour, because we're trying to find the score of a student that studies for 1 hour. So it's 1 right here, boom. And so we see that this correlates right over here on the dependent side, right here. It has a value over here, because here on the line has a value right there. So that means that the score is equal to K. K is a constant that we don't know yet, right? K times the study time plus C. So the Y on the Y value on the line of best fit is the prediction. Here we have, oh, sorry. Okay, hold on. Okay, so it's the best prediction. So here we have the value of 1, and here we see that it also correlates with the Y value over here. So 1 linear unit below 60, so 1 little box below 60, and we know that the unit of Y is going to be 5 points, so it's basically just going to be 60 minus 5, which is going to be 55. So we can say here, using this graph, that the best prediction of a score of a student that studies for 1 hour is going to be 55 points on the test. Okay, this is going to be our last question, and then I'm going to hand it over, and then we have a little break. So thank God. All right, so the scatter plot shown plots the relationship between the latitude of cities and their average January temperature, right? So what is the best estimate of the average change in temperature associated with the 1 degree increase in latitude? What is this asking? You might ask. This is just a bunch of baloney. I don't understand what it's saying, but we have to understand what this is asking, right? So first of all, let's understand our unit. So, Danawi, can you tell me what the unit is on the x-axis? Danawi, can you tell me what the unit is on the x-axis? Danawi, if you're there. Danawi, haven't heard it from you all class. All right. Can Layla, can you tell me what the unit down here is for 1 box? Layla.
Yes, the unit.
Yeah, the unit down here on the x-axis or on the independent, what unit is for 1 box?
Per box, what the unit is? Like what the measurement increments?
Yeah, the increment.
Oh, 5 increments of 5?
Yeah, it's 5. Very good. Very good. And can you tell me what that same increment, what that little box is going to be for over here for the independent axis? What is that?
Wait, you said what are the increments for the independent axis?
Yeah, for the dependent axis, so the Y. So over here, how much does it go up 1 box? Up 1 box.
Wait, 1 box is 5, but it goes by 25s.
No, but how many boxes are between 25 and 0 over here?
5.
5. So it'd be 25 divided by 5, which is equal to what?
5.
5. Very good. So we have 1 unit Y is equal to 5 degrees. So this is basically just 1-to-1 on the units, right? So it's 5 degrees here and 5 degrees over here. So Y equals mx plus c. This is just a basic slope equation, right? And so we have here this equation. We can apply it over here, right? So temperature is equal to the temperature outside here, or the temperature in Fahrenheit, is going to be equal to m, which is some constant, times the latitude, as in like how high it is, which is the independent value. So we have the independent value down here and the dependent value up here, right? And so that means that x, this is going to replace x because x is the independent value, and it's going to replace y because this is the dependent value, right? Plus c, plus whatever thing you want. So what is the average degree change? What is the average change in temperature associated with 1 degree increase in latitude? So if this goes up by 1, how much does this go up by? How much? So if the latitude over here goes up by 1, how much does the temperature go up by? So we can see here that this is asking about the slope, because this is the x value. This can be whatever x value, right? But then if we multiply by here, that's going to give us our new thing, right? So that's basically asking for the slope. This is asking for m. Whenever you see a question that asks like, what is the best estimate for the average change in something associated with another change in anything, that is going to be asking for the slope. So that's going to be asking for m. All right, so first of all, let's draw the line of best fit. So we're going to draw the best line of fit, and it's going to be basically this. So we have to find usable points. So here we see, oh my gosh. Okay, I'm so sorry. I'm so sorry, Pamela. Okay, it's gonna only be a little bit, only a second. Okay, so we have the find usable point. So we see here that the line of best fit intersects the grid roughly around here. That's basically a usable point, and roughly around here, and roughly around here. So we're gonna use two of these points. I don't remember which ones they are. This point, okay, so we're gonna use this point and this point down there. So if you guys know how to use the slope, we're just going to use the slope formula. We're going to denote this this point, which is going to be 30 and 50, because we have here, I'm trying to move this thing. So we have 30 right here, 50 right there, and 50 and 0, because we have on the x-axis 50 and on the y-axis 0. We're going to find the slope, which is going to be this equation. You guys can look over this later. So it's going to be 0 minus 50. And so that means that the slope here is going to be negative 50 over 20. And so that means that the average change in temperature associated with 1 degree increase in latitude is going to be negative 2.5 degrees. So that's what that's saying, is basically for every latitude that this goes up by 1, the temperature drops 2.5 degrees. So that's basically what it says. So thank you so much, and feel free to ask any questions on anything you want to say here.